Well, it's a pleasure to be here. Thank you for the gift. So we'll talk about black holes, entropy, and quantum information. I was asked to make this talk generally accessible to people outside physics. And for that reason, I will start with a general discussion of black holes. So a brief summary of the talk is that black holes are very confusing. Everyone who has worked on black holes has got confused, and then some people came afterwards. They found other things, and so on. So black holes were first found in solution of general relativity by Schwarzschild. The creator of general relativity thought that they weren't physical solutions, that they were just mathematical curiosities of no physical significance. But then it was shown that they were unavoidable. And then, even more surprisingly, they are not even black, so the name was chosen incorrectly. And Hawking said that they might imply that quantum mechanics is incompatible with gravity, so there were very big confusion. And now a bunch of us are working on trying to understand how black holes are compatible with quantum mechanics. And using some theory called string theory, one can see what's involved in this comparison, and I'll be talking about some of these issues. But there are still many puzzles, especially regarding the black hole interior, that we do not understand. That's a little bit of a brief outline of the talk, so now I'm going to start from the beginning. So gravity, first we have to say a few things about gravity. Aristotle said that heavier objects fall faster, and Galileo realized that everything falls in the same way once we remove the effects of air resistance. And Einstein realized this, had his happy thought. Einstein's happy thought was the idea that when you fall freely, gravity disappears. So if you are in some space-time, or we are sitting here in this room, and we remove the floor, and we start falling freely, we lose the effects of gravity. We don't feel any particular force. And so he suggested a new law of physics, which is the so-called Equivalence Principle, which says that if you are falling freely, the laws of physics should be the same as if you were in locally flat space without gravity, at least locally. That's the Equivalence Principle, and he incorporated, well, this is what astronauts feel in space, but Einstein incorporated this into his theory of general relativity, which says that gravity is due to the geometry of space-time. If you have a heavy object, it will curve the space-time around it. And a second particle, so if you have a test particle, so a small light particle, it will follow a trajectory of maximal lifetime along that space-time. Now, something important is that gravity changes the flow of time. So time flows differently for two observers in a gravitational field. So for example, we have a person in the upper floor of a building and a person in the lower floor of the building. Time will go more quickly for the person on the top floor of the building. Now, for an actual building, this is in the gravitational field of the Earth, this is a very small thing. It's just a part in 10 to the 15, so it's very small. But with current atomic clocks, it can be actually measured. And the record is about 3 centimeters in height difference. Okay. Now, if you have, so there is a kind of version of the twins paradox involved in this. So you have two twins, and one of them is near a very massive body for a while, and afterwards one will be older, the other one will be young. Okay, so now so what is this geometry that Schwarzschild found, and why it was surprising? Well, he found basically the geometry which is a solution of the vacuum Einstein equation. So he took so we said that Einstein equations relate the curvature of space-time to the amount of energy present in the space-time. These are local equations, so the curvature at a given point, or roughly speaking, the average of the curvature, is proportional to the amount of energy that you have in that region. So in particular, if you don't have any matter, so then that average curvature should be 0. And then you can solve the equations with spherical symmetry with those conditions, and that will give you the gravitational field or the geometry, the whole space-time geometry, outside the massive body. So we can have, for example, a star where there is some matter that warps to space-time, and that creates a whole geometry outside, and Schwarzschild found the geometry outside. And this geometry tells us many things, but in particular, it tells us the rate of flow of time. So if we have a clock far away, let's say flowing at unit rate, so that sets the flow of time far away. Then if we have someone at some radial position, let's say on the surface of that star, it will feel the clock going at a slower rate. And also will feel some weight, right? So as we're feeling right now. Now, if we had a star that becomes smaller but with the same mass, then the geometry in the exterior would be the same, and we would be exploring a bigger region of the Schwarzschild geometry. The geometry inside is not the one given by the Schwarzschild solution, because that comes there is some matter, the matter of the star, and it's a different geometry. But for now, we will talk about the geometry outside the star. So if we now have a more compact star, then the flow of time will be even slower. For example, on the surface of a neutron star, the flow of time is 70% slower than far away. So that's a very compact star that we can have in nature. And a person standing at the surface of such a star would feel a much larger weight than the person that would stand at the surface of the star at this position. And then the surprise was that there is a minimal radius. So for a radius, if the radius of the star was smaller than a certain radius, which we now call the black hole radius, then if the star had that radius, or smaller, then if you sit at that position, the flow of time seems to come to a stop. So the time goes infinitely slower for an observer who's just sitting at that position. And furthermore, someone sitting at that position would feel an infinite weight. So it would be infinitely heavy, an infinite force of gravity in this situation. So, and the fact that the geometry has that feature is what made Einstein think that this couldn't possibly have physical relevance. I mean, it couldn't be that the gravitational force would be infinite, that you would this couldn't possibly arise. Okay? That's what he thought. But something important about this observer is that this observer is not falling freely. He's sitting at that position. He feels an infinite force. But we could ask another question, which is what would be felt by someone who's falling freely in this position? Would he also or she feel some infinite force of gravity? So if they fell freely, actually what you find, what people realized later, was that this surface, which we now call the horizon, is actually a completely smooth surface. Nothing special happens. You don't feel anything special when you cross the horizon. But you enter a new region of space-time. And this new region of the space-time is inherently sort of time-dependent. Inside the black hole, the geometry looks like a collapsing universe. So it looks as if the whole space-time is collapsing. It's a big crunch. So there's a little big crunch inside each black hole. So if you were someone who's falling in, so don't feel anything special when you cross the horizon. However, there's a region here at the end of time. So it's not a point inside the black hole, but it's a point in the future. In the space-time region to the future of the space-time region, which is past the horizon. And there, that region of space-time is collapsing, and the gravitational tidal forces become very large, and that means that they will stretch you, and what people call this is spaghettify. So you're made into spaghetti. Okay? So it's not good to go through to the singularity. Okay? So if you are going to do an experiment with black holes, it's better to sit outside. Okay? Stay outside, not going. Okay, so that's, as I said, it looks a bit like a big crunched space-time. And I mentioned that the singularities really should be viewed as being in the future. and not somehow as a place in space, but as a place in time. Now there is an analogy that is often made between horizons and this particular physical setup, where you think about a river, where, and I think Bill Unruh, did you originate this analogy? Yeah, so Bill Unruh sitting here originated this analogy. So where you have water flowing in a river, and the velocity of the water increases as you approach a waterfall. Okay. Now in this river you have some fish, and the fish can swim with a maximal velocity which we call c, which is analogous to the speed of light. And if the velocity of the water is less than the maximal velocity at which the fish can swim, then the fish can swim upstream and can avoid falling into the singularity. But there is a point here along the river where the velocity becomes equal to the maximal velocity at which the fish can swim. And if the fish was here, then it would just stay stationary at that position. And on the other hand, if it started out here, no matter how hard it tries to swim, it will end up at the singularity. Now, if the fish cannot look to the shore of this river, the fish would not notice anything special happening at this position. Okay, would not have any way of knowing that point was special. And so that's the idea. So in that sense, the horizon of the black hole is special. It's not any special point. In summary, so once you cross this horizon, you cannot get out. It was later learned that stars can collapse into black holes, and that there are objects in the sky that seem to be black holes. So let me just, since we're in the remainder of the talk, we're going to talk about more theoretical aspects. Let me just say a few aspects of about real black holes. So there are two types of black holes that have been, for which we have evidence for. So one type are the black holes made by the collapse of massive stars. They have a mass of order stellar mass, and of order a few times the mass of the sun, and these type of sizes. And then there are black holes at the center of galaxies, which can be very big. They can be of the order of the size of the solar system. How do we see them? Well, we can see them because when matter falls in, it heats up and it emits light or some other type of radiation. And by looking at that radiation, we can infer the presence of a black hole. We can also see the gravity waves produced when two black holes collide. So one example of the first effect is this picture that I'm sure maybe most of you saw, of the picture of the M87 black hole from the Event Horizon Telescope. Previously, there had been effects that were thought to be due to black holes, due to jets coming out of the centers of galaxies. So these are huge jets, much bigger than the size of the galaxy. And this is another nice picture. And then the other one comes from the other method by which we infer the existence of black holes, is by looking at the gravity waves that are produced by collisions of black holes, which we see in the gravity wave detectors, as you probably all heard about. Okay, so that's the end of the phenomenological aspect of black holes. So now we are going to start discussing theoretical aspects of black holes. Okay? And these are interesting conceptual aspects. So let me just mention and emphasize a few interesting and important properties of black holes. The first one is the property of universality. So the final shape and form of a black hole is independent of how we form the black hole. So that's not true for stars, for example. We can have all kinds of stars. We can have yellow stars, orange stars, blue stars, etc., of different shapes, of different quadrupole moments, etc. If they were to collapse to black holes, they would form just very simple geometries, which are characterized purely by their charge and angular momentum, and the mass. So in practice, it's really typically, if you don't have any charge, you really have angular momentum and mass, and that characterizes these black holes completely. So out of all the complexity of the star, all that is lost, and you are left with very simple shapes, which are called the rotating black hole solution. It's a geometry which Roy Kerr found analytically, and well, that's the endpoint of the evolution of many massive stars. A second interesting property is that is the following. Imagine that you have this collision of black holes that we discussed, for example, that emits gravity waves. The fact that it emits gravity waves implies that the mass of the final black hole will be smaller than the masses of the initial black holes, because some energy went into the gravity waves, so the mass of the final object has to be smaller than the initial masses or the initial energies of the mass is equal to energy, so I'm putting C equal to 1, of course. But on the other hand, so the mass of the black hole decreases, but on the other hand, Hawking discovered that the area of the black holes always increases. So you cannot have a situation where you collide two black holes and you're left with nothing, for example, that all the energy is emitted into gravity waves. You cannot have that situation because the final black hole would have zero area, but the initial black holes have non-zero area for the horizon. And the properties of light rays near a black hole horizon are such that the areas should always increase. So this is a very simple property of a very complicated solution. So solving the equations for these black hole collisions is something that is quite difficult, and until very recently, people could not do it. So the first one, I think, to manage to do this calculation was Franz Pretorius, about maybe 10 or 15 years ago. So that was very challenging. But on the other hand, those complicated equations have a very simple property, which is this area increase theorem, okay, that follows from some aspects of the geometry. Now, so far, these two properties that we discussed, the universality and the area increase, are properties that hold according to the classical theory of relativity, which is just a classical theory where no quantum effects are taken into account. Now, when we include quantum mechanics, there is a new surprise, which is the fact that black holes have some temperature. And in fact, black holes can be white, so we can have white black holes. So Hawking found that black holes emit radiation at a given temperature. And the temperature depends on the size of the black hole. So the smaller the size of the black hole, the higher the temperature. Roughly speaking, the thermal radiation that comes out of a black hole has a wavelength which is proportional to, well, is more or less equal to the size of the black hole. So as you make it smaller, the wavelength becomes smaller, and the temperature, therefore, becomes higher. So had a black hole would look black if it is very big. If it becomes smaller, it will look red, and if it becomes even smaller, it will look white. So, I mean, it would really look white to your eyes. So you can have a white black hole. So here are examples of black holes, temperatures of black holes with various masses. So if you had a black hole of the mass roughly comparable to the mass of the sun, which are the type of black holes that are produced by stellar collapses of stars, they have very, very tiny temperature. This temperature is much smaller than the temperature of the CNB. So such black holes are not emitting Hawking radiation. They're mostly absorbing the radiation from the CNB. Okay? So this is not an effect that you are going to see in a black hole that has the mass of the star. But imagine you had a black hole of the mass of a continent. Then it would have a temperature of about, well, a temperature corresponding to white light, and it would have a size roughly of a bacterium. So if you had such a black hole, it would actually look white. And you can calculate how much an object, how much you can use the Stefan-Boltzmann law to calculate how much light an object of the size of the bacterium at this temperature would emit. And you can check that you can see it with your own eyes. So you can actually, you would be able to see it, and it would look white. Also, you wouldn't be able to stand very close to it because of the tidal forces. So you have to stand at some distance. I once made a little model with an LED that would emit this power, the power that was emitting. And I tried to present it at a lecture, and it was completely underwhelming because no one could see it. But okay, so Now, why do we have this phenomenon of Hawking radiation? So it's related to quantum mechanics, but more specifically also to relativistic quantum mechanics, or sometimes called quantum field theory. So it's the joining of quantum mechanics and special relativity. In this theory, particles can be created and destroyed. And according to this theory, the vacuum is also a somewhat complicated state where particles might be created and destroyed all the time. But in this theory, there is a certain law, a certain thing that should happen, is that negative energies are not allowed. So any physical true particle should always have positive energy. Now, and there is a kind of policeman that ensures that all the particles that are created have positive energy. But the policeman is restricted by the Heisenberg uncertainty principle. This is a qualitative explanation, by the way. And so if the negative energy particle exists for a time smaller than 1 over the energy, or h bar over the energy, then the policeman lets it go. Okay. But there is no net particle creation. So if a negative energy particle is created, it can only exist for a very short time and be annihilated against a positive energy particle. So you can have some negative energy for a time, but they have to. So the net effect of this is that in flat space there is no net particle creation. Now in the presence of the horizon, there is a new thing that happens, which is that so a particle can be created with a pair of particles can be created, and the particle outside might have positive energy, and the particle inside might have negative energy. But the notion of energy for the inside observer is different than the notion of energy from the point of view of the outside. So what looks like energy from the point of view of the outside observer looks like momentum from the point of view of the inside. And so for the policeman that lives inside, this particle that from the point of view of the outside has negative energy, from the point of view of the inside has negative momentum. And the policeman has no problem with this, right? So lets it go, fine. And in the end, the net result is that you are emitting particles with positive energy. So that's a qualitative explanation of the Hawking radiation process. Okay, so there is this new phenomenon. It's a phenomenon that was predicted theoretically. It's a very solid prediction, and it hasn't been observed experimentally for reasons that we just said, but we think it's a phenomenon that should be there. And there is a closely related phenomenon that occurs in the beginning of the Big Bang, which is, we think, is responsible for the creation of primordial cosmic fluctuations. That is actually what seeds the formation of galaxies and so on. So the type of phenomenon, these two phenomena, Hawking radiation and primordial fluctuations, are conceptually similar phenomena. And the second one, the cosmic fluctuations, is something that is crucial for describing our universe. So, and we could say that the cosmic fluctuations certainly have been observed. The idea that they were created using a phenomenon similar to Hawking radiation is a theory, is part of the theory of inflation. And well, I view it as, well, the question of whether that's the only explanation or not is being debated. But, so let's see what this implies for a black hole. So if you have a black hole in flat space, so at where the flat space is at 0 temperature far away, the black hole would start losing its mass, and it will have a finite lifetime. So here I'm going to just record the lifetimes of various black holes. So black holes with the mass of the sun of the Earth will live much longer than the age of the universe. And a black hole with an ordinary mass would evaporate in a very tiny fraction of a second, so it would be worse than a nuclear bomb. And a black hole of a mass of roughly a mountain, produced at the beginning of the Big Bang, would be evaporating right now. And in principle, there could be very tiny black holes produced in particle accelerators. They would decay very quickly. But in particle accelerators that have been constructed so far, there is no evidence of such things. But in principle, in some theories, some very special theories, it could happen. Now, there are a couple of problems, of theoretical problems, that the black hole temperature, the existence of black hole temperature poses. And I'd like to describe these two problems now a little bit. So one question is, why are black holes hot? The black hole entropy problem. And the other one is the problem of information loss. So we know temperature is due to the motion of microscopic constituents. And there is an associated notion of entropy, which is to we obtain from, and there's a first law linking the change in energy to the change in entropy. And given that we know the temperature of the black hole as a function of the mass that was calculated by Hawking, then one can calculate the entropy, and the entropy turns out to be equal to the area of the black hole horizon. And so there is, I set C equal to 1 in this formula, and K Boltzmann equal to 1. But there is a 1 over h bar here, which we didn't set to 1. So this entropy is, has to do with quantum mechanics. In the classical limit, this would be infinite. And also when the Newton constant becomes very small, it would be infinite. This combination of a g Newton and h bar, units with c is equal to 1, is a distance. So it's the area in units of the so-called Planck distance, which is 10 to the minus 33 centimeters. This is a very tiny distance. So these entropies would be huge for macroscopic black hole. But one interesting thing is that now with this formula, one can reinterpret this area law that Hawking had derived just looking at solutions of Einstein's equations as due to the second law of thermodynamics. So the idea that entropy should increase. Okay? So somehow Einstein's equations know about the second law of thermodynamics. So this should be first kind of surprise. Okay? You should be surprised about this. So I'm not sure if I'm conveying the sense of surprise. Maybe you heard this many times. So okay, yeah, black holes area. But it's very surprising that Einstein's equations, which are deterministic equations, some field theory, some waves, gravity waves, the formation of space-time, and so on, they would know about the laws of thermodynamics. It's surprising. But so that's the one surprise. Now we have an entropy, and if in any physical system that has some entropy, we would like to understand what the constituents are. So what makes the entropy of this black hole? And since black holes are universal, they have universal features independent of the matter that made the black holes in the very beginning. The entropy should just be a property of spacetime itself. Now, what is the information loss problem? So this is a problem pointed out by Hawking in the 70s. So we can form a black hole in different ways, but it always evaporates in the same way. So we can throw information into a black hole. The black hole emits thermal radiation with no apparently no information about the stuff that went in. And so if we had quantum mechanics, we should have a precise description for what comes outside, at least in principle. And the thermal aspects should arise only due to some approximation. So if you burn a piece of coal, or you burn a piece of paper, in principle, by collecting the gases, you could figure out what was written in that piece of paper. Of course, in practice, it will be very difficult, but we think it should be possible in principle. But here, the one problem is that it looks like even in principle it would not be possible, because when we throw this piece of paper inside the black hole, that piece of paper is in the black hole interior, and it looks like the radiation was produced from the outside. It has no information. So the idea is that there should be some subtle differences in the outgoing radiation, which carry the information about how the black hole was made. Now, in order to try to understand whether what really happens and how to resolve these problems, we need a theory that puts together quantum mechanics and gravity. And one such theory is string theory. I will not describe all of string theory. I'm only going to mention some few things. First is really should view it as a theory under construction. It's a theory that attempts to, its goal is to understand quantum gravity, so the quantum mechanics of space-time. So how does space-time behave in a quantum mechanical way? It's a theory that reduces to Einstein's theory under ordinary circumstances. That means to say at low energies or long distances. And one aspect that was found in this theory is that it can describe in certain simple universes with negative curvature. So there are very simple, let's say, toy model universes in which this whole theory of quantum gravity is supposed to have a complete description. Let me try to explain that point. So this is sometimes called holography. So we can describe the interior of certain spacetimes in terms of a theory that lives only on the boundary of the spacetime. This works particularly nicely for spacetimes with negative curvature. The boundary theory is a theory of interacting particles, strongly interacting particles, but without gravity. So it's a conventional quantum theory. So we don't have to worry about the dynamics of space-time. And that's supposed to be equivalent to a theory in the interior with dynamical gravity. So roughly speaking, it's something like this, where you could have some object living in the interior, and that object is described by a collection of particles on the boundary that are strongly interacting. This funny motion that I try to represent here tries to represent the strong interactions between these particles. They should be very strongly interacting. And also, similarly, if we have a black hole in the bulk, a black hole is described by a large collection, a fluid of strongly interacting particles. So I should have put more of these particles, but I ran out of patience. You should view this as a fluid made of lots of these particles. And that's the description. So in this description, then, the temperature and entropy of the black holes are the temperature and entropy of these particles that live in the boundary. So these are setups where we know what the theory on the boundary is, and we can independently calculate the entropy. So we do a calculation in the strongly coupled system. We can calculate the entropy, and then compare to the area of the corresponding black holes that we obtain by solving Einstein's equations with some specific matter content and so on. And these two calculations, in the cases where you can do them, they agree with each other. So this theory on the boundary obeys the rules of quantum mechanics. And so then if you accept this correspondence between the dynamics of the boundary and the interior, which is really truly a conjecture, then the black hole in the interior should also be consistent with quantum mechanics. Now, one funny aspect of this relationship is the idea that we have an immersion geometry. So we have a quantum system, which in this picture I've tried to represent as a one-dimensional line. So imagine a one-dimensional quantum system. And we have an extra dimension that's where gravity lives, in the extra dimension. So in order to try to explain how this works, we're going to see a kind of analogy. So this will be something analogous, and then I'll try to make this analogy a little better later. So it's a verbal analogy. Imagine that you have a phrase. For example, I took here a random phrase. If a man does not keep pace with his companions, perhaps it is because he hears a different drummer. Okay? So that's a sentence, an English sentence. And when we hear this English sentence, or when you were in grammar school and you were asked to do the grammar of this sentence, you would separate the sentence into different pieces. So you heard some sounds, and you separated the sounds into words. You did all this in your mind. And then you group words together into phrasal, different grammatical structures of higher level. So we have the first phrase, the second phrase, etc. And also, in this situation, there are long-range correlations between different words. Like, for example, the word man, the word his, and the word he are correlated. Or the notion of keeping pace and drummer are also correlated in some way. So that's a well-formed phrase, has correlations at very different length scales. So the idea is that you can think of all these correlations as giving rise to an extra dimension, right? So objects that are deeper in the extra dimension are the more abstract things that you see in this sentence. Okay. So the first part of the sentence is some idea that you're talking about. The first sentence is this whole thing, and that's deeper in the analysis. Okay. It's not the most superficial thing that you find, but it's deeper in the analysis. That somehow lives in an extra dimension. The extra dimension of let's call it meaning. The extra dimension of meaning. That's the extra dimension. Of course, different sentences will have different structures of words and so on. They might be different in the interior. So the analogy is roughly that the sentence is similar to the state of the quantum system. So the state is really a quantum mechanical state. And the structure of the correlations, these are quantum correlations or entanglement that different pieces of the quantum system has. And entanglement or correlations at higher levels that involve longer distances in the sentence live deeper, correspond to features that are deeper in the bulk of the extra dimension. In the same way that we could have let's say, correlations between different, like the word man and his and so on that we had in the previous sentence. Those could be some extra correlations that correspond to particles that propagate in the extra dimension. Okay, so those are some extra things that we have. So there's some kind of background thing that has to do with the meaning of the sentence and the way the sentence is made, and then some longer distance correlations that have to do with particles propagating in that geometry. Now, what is a black hole? So imagine you take the sentence again, and you start changing the sentence. So you change it randomly. And so in this case, we changed a few words. And because we changed a few words, some correlations were lost. And the sentence, even though it makes sense locally, at some global sense, it doesn't make sense. It doesn't look as good as the previous sentence. Okay? It doesn't have those correlations. And we can continue changing the words in a more random way. And then the sentence starts making less sense. And we can analyze it up to a certain level, but not beyond that. So the level at which we can analyze it, we call it the black hole horizon. Okay? And as we start changing the sentence more and more, the black hole horizon grows. And so the idea that if we start changing the sentence in a random way, the horizon will grow. And the second law of thermodynamics is just a statement that if you just change the sentence randomly, the changes are more likely to mess up the sentence. If we change a sentence randomly, we are more likely to mess it up than to make it nicer. Okay. Now, suppose that this changes. So imagine that this final sentence that we got here was actually produced by a reversible process. Let's say an encryption algorithm, right? So we have something that, given an original sentence, gives us by a reversible algorithm a new sentence. Then in that case, we would be able to revert. If we knew what the algorithm, if we don't know what the algorithm is, we would say it's a black hole, right? We don't know what this is. We can't find any meaning. But if we knew what the algorithm is, then we can go back and find what the original meaning. So if we can reverse the process, we can recover the original sentence. And that's what we mean by recovering the information from the black hole. So the idea is that the laws of physics on the boundary change the state of the boundary system in a reversible way, because the laws of physics are reversible. And so it's analogous to this encryption algorithm. It's reversible. And so in principle, we can undo the formation of the black hole and recover the information if we knew, from this boundary description. OK, so now I reviewed a few features of black holes, and I've described how in certain circumstances we can view a black hole from the point of view of the boundary theory. There are some concrete constructions in some simple models of gravity. And the take-home message is that that if you have a black hole and you see the black hole from the outside, then it can be described by a quantum system with s degrees of freedom, or s qubits, where s is equal to the area and proportional to the area. And this system evolves according to a unitary evolution as seen from the outside. So we can take a black hole, which is a mysterious object, and the idea is that we can replace it by some suitable system of qubits with some Hamiltonian. Okay? Now, this is a picture that we think is valid in general. We understand it. We understand what these qubits and what this unitary evolution is only for some very specific gravity theories. But as we saw, black holes are generic phenomenon. They don't depend on the details of the gravity theory so much, the details of the standard model and so on. So we think that these lessons that are being abstracted from the simple models also hold in principle for general models. And the most, let's say, abstract lesson is this one here, that if you have a black hole, you view it from the outside, you should be able to think of the black hole as a quantum system with this number of degrees of freedom and evolving unitarily. And so far, there is no thing that was, no question you can ask about the black hole that would contradict this picture. Okay. And there are many things that make sense when you think about this picture. And I don't have time to discuss all of them. So I'm going to call this a central hypothesis or central dogma. So central dogma in the sense that biologists use it. That biologists think that in life, information goes from DNA to to RNA, etc. So we think that if you view a black hole from outside, it's described by a quantum system. It's supported by some facts, but, well, it's an assumption that we'll make from now on. Now, this tells us what the black hole is from the outside. But what about the inside? So the inside is a little more mysterious. And before talking about the inside, so let's just do a little bit of taxonomy of the inside. So again, the biological approach will just collect specimens and see what kinds of insides black holes can have. Okay? So simplest inside is the one that is produced by gravitational collapse. So this is based on this paper of Oppenheimer and Snyder in 1939. They considered a shell of dust or some dust ball, and they noticed that this dust ball will collapse and form a black hole. And so outside the shell, we have a portion of the Schwarzschild geometry. So this portion here is a portion of the Schwarzschild geometry. I should explain probably what these diagrams mean. These are called Penrose diagrams or space-time diagrams. Here we're considering a spherically symmetric situation. So each point on this diagram corresponds to a two-dimensional sphere. And then the horizontal direction is roughly related to the radial direction, and the vertical direction is roughly related to the time direction. Okay? Now, this is a representation of the space-time where we rescaled the space and time directions in such a way that the light rays go at 45 degrees. So we just made rescalings that preserve the angles or the directions of light rays. And so in these diagrams, for example, the horizon corresponds to the last light ray that so a light ray that starts just at this point can make it out to infinity. So this region is far away at infinity. And so a light ray that starts here can make it all the way to infinity. A light ray that starts inside will end up at the singularity. It would be like the story with the fish and the river and so on. And this light ray corresponds to that fish that is swimming exactly at the velocity that the water has at this point. So it will not get out to infinity or fall to the singularity. The matter crosses the horizon and falls into a singularity. And so here we have this exterior region. And inside here is not the Schwarzschild geometry. This is a geometry with matter. But at this line here, the two spheres shrinks to zero size. That's like the origin of R3, right, of three-dimensional space. And so this is a perfectly regular point. But we just have one exterior and this one interior region. Now, it turns out that there are other geometries that are allowed by the equations. And there are many geometries that are allowed in principle that we cannot make. Yeah, I'm not going to explain now how to make these geometries, but they are simply geometries that are allowed by the equations. And if we're going to collect possibilities, we should also collect these geometries. And there are various ones, but the perhaps simplest one is the one that actually Schwarzschild found. So if you take the Schwarzschild solution and you extend it completely, so we said that so the solution in the Schwarzschild coordinates, the one that Schwarzschild found, describes the region outside the black hole. So it describes this region. It looks, again, these are space-time diagram. This is far away in four space-time dimensions. Each point on this diagram is an S2, and the horizon corresponds to these two lines. Then there is some interior region, and surprisingly, there is actually a second exterior region. So the full solution, once you analytically extend it past all their coordinate singularities, or said differently, you take that solution and you write it in better coordinates. So general relativity sometimes is difficult to see the nature of the solution unless you choose. Well, if you choose the right coordinates, then it's easy to see. And if there are some coordinates you can choose, chosen by Kruskal, where you can clearly see that this is the geometry, that the whole space-time corresponding to the original Schwarzschild solution. So the Schwarzschild solution does not describe one black hole, but two black holes. So there is far away, we have some R4, there is another R4. And so there are like two joint black holes that are sharing a single interior. Okay? So that's a weird solution. But it's allowed by the equations. In fact, it was the first sort of non-trivial solution that was found of Einstein's equations. Right? So if you did, now some people tend to dismiss it because they say, okay, well, I don't know how to make this solution, so maybe it will not form in nature. Okay, I mean, some of these things were also said about the Schwarzschild solution I told you, and about black holes, that they are irrelevant. So we are going to take this solution seriously, and we're trying to see what other things could imply. So in other words, any theory of what the interior, how we should think about the interior, how we should think about the black holes, should not simply work for the solution for collapse that are produced by collapsing stars, but it should work for for all solutions. Or you should have a good reason to not consider this solution. Now, I'm going to describe now a little bit the geometry of this surface here. So this is a surface at an instant in time. It's called the Einstein-Rosen Bridge. It occurs at one particular instant in time. The geometry of that solution is roughly like this. So there is some three-dimensional space far away. And then as you go closer to the horizon, the two-sphere shrinks to some minimal size. And then it expands again on the other side into another three-dimensional space. Okay? So that's the nature of the spatial section. So the radius of the S2 here is finite and equal to the area is equal to the horizon area. Now, so it looks a bit like a wormhole that connects very far away regions in space-time. That's the connection, the space-like, along a space-like direction. But this happens, and it's fine as long as we move along the spatial section, or in other words, at an instant in time. But actual particles travel at most at 45 degrees in this diagram, right? So we cannot move along a surface with constant time. That would be moving faster than the speed of light. Okay? So if you were able to move faster than the speed of light, you could go from this side to that side. But unfortunately, we cannot go faster than the speed of light. So the best we could do is move at the speed of light. And then in this case, if we start from the left side, we can go into the interior, but we cannot make it to the other side. Okay. So these are called non-traversable, not traversable wormholes. So we could have these two black holes in the original Schwarzschild solution. They are in two somehow separated universes. But there's a very similar solution where they're in the same universe. And so we can have two black holes that are far away connected through the interior. Now, this is a very special solution, and if you find two black holes in nature produced by gravitational collapse, they will not be described by these geometries. They will be described by two copies of the previous geometry we discussed. So this is a weird situation that is allowed by the equations that you could in principle have, and we are trying to understand it. Now, from the outside, each of these black holes is supposed to be a quantum system. Okay? So this central hypothesis that we said, or central dogma, would tell us that we can replace each black hole by a collection of qubits. Okay? And now the fact that they are connected is supposed to be related to the fact that these two sets of qubits are in a particular entangled state. So the connection is due to the entanglement between the two. That's the idea. And more specifically, we know specifically which state this Schwarzschild solution should correspond to. It should correspond to the so-called thermofield double. So you take all the energy levels of the left system and take the energy levels of the right system, and then you sum over them with these thermal-looking factors to produce the so-called thermofield double state. And the idea is that if you had the quantum system corresponding to the black holes in this particular state, then the geometry would be that of the original Schwarzschild geometry. So we have somehow some interpretation for what this geometry is. This was originally done by Werner Israel in the 70s. And we think that this connection between entanglement and geometry should be something quite general. And we've called it ER equal to EPR. So EPR relates to the Einstein-Podolsky-Rosen paper that introduced this notion of entanglement in quantum systems. And Einstein and Rosen is the paper that showed that the Schwarzschild solution contains these two connected. I mean, it really describes two black holes connected through the interior. curiously, both were written the same year, not far apart from each other. Yeah, it's interesting that they are related. Okay, this example that we've seen is just some connection between entanglement and geometry. And the idea is that in this notion of holography and in thinking about black holes, it's useful to think about entanglement and how entanglement in the quantum system translates into geometrical properties of the black hole in the interior. This was just one example, but there are many things that are related to this. In particular, this verbal analogy that I discussed to you, that I described to you, there is there the correlations were purely classical, but we think that in the case of holography and so on, we are talking really about quantum correlations. And there is actually a way of thinking about correlations of quantum systems that's something called tensor networks, via something called tensor networks, where it is a construction that has many of the features of geometry. So it's very similar to what is happening in geometry, though not identical, at least so far. Now, I would like to go back to this verbal analogy and just say, well, this is just an analogy for the wormhole that connects the two spaces. So we can imagine two sentences that are in two different languages, here Spanish and English. And so the words are not the same, but the meaning is the same for both of them. They both share the same meaning. So if you start doing the analysis of this sentence, at some point they are sharing exactly the same meaning. Okay, so now it's the time to tell the story of Romeo and Juliet. So we are sometime far. So this story is trying to explain in what sense. So we have this funny geometry, and the funny geometry is, which is the Schwarzschild geometry. It's we have two black holes that are sharing the interior. But I told you that we cannot send the signal from one to the other. So in what sense are they sharing the interior? I mean, how can we see some more surprising effect? Well, one thing is that you can have observers that fall from the go into the two black holes, and they meet in the interior. Okay. So in fact, Romeo and Juliet were going to use this. So we are sometime in the future, and there is the story of Romeo and Juliet, where their families don't like each other, so they put them in different galaxies. But they are very determined. They know a lot of physics, and they know that if they start exchanging qubits that are entangled, they could eventually produce a pair of entangled black holes. And they have a lot of time, and they can do this. And they produce the entangled pair of black holes. And the idea is that if they produce such entangled pair of black holes, then and they decide to jump into those black holes. If you look at the bottom figure, their families see that they jump into a black hole and they die. Okay, so they committed suicide. And that's what the narrator of the story actually wrote, because he stayed out of the black hole. But if you look at the top picture, what happened was that after they constructed this situation with the entangled qubits and so on, this is very difficult to do, by the way, but let's imagine they were very smart and they managed to do it. They would, when they jump into the black hole, they actually meet inside, and they can live for a while inside. Eventually, in this version, they fall into a singularity. Okay. So this is a version you will not see in the movies in Hollywood. So it's a not happy ending. Okay. Now the question is whether there is a more interesting story, right? Are there other things that Romeo and Juliet could do with these black holes, just to avoid their parents keeping them apart? Okay. So they know, I said they know a lot of physics, so they actually read another paper. So they read a paper by these authors here, by Bennett et al., on something called quantum teleportation. So quantum teleportation is something you can do when you have entangled qubits. So let me give you a very quick summary of what quantum teleportation is. So imagine you have an entangled qubit, just a single entangled qubit that is shared. So Bob has one qubit, Alice has another qubit. They are in a maximally entangled state. Now, Charlie wants to send a message. Okay. So then you can get this Charlie's qubit and mix it thoroughly with this other qubit by a unitary transformation. It has to be unitary transformation that mixes them thoroughly. I will explain what mixing thoroughly means. And then you measure those two qubits. You get two classical bits of classical information. So you do this measurement. And then after doing the measurement, you send the classical information to Alice. And Alice applies another unitary transformation to her qubit. And then she gets a qubit here that will be in exactly the state that Charlie's qubit was at. Okay? So that's the phenomenon of quantum teleportation. And the resources needed were with this entangled pair and 2 bits of classical information. Now, quantum teleportation is a bit surprising because if I told you that we want to send a qubit from here to somewhere else, right, to some distant party, to specify a qubit, it looks like you need to specify an infinite number of numbers, right? It's a direction in space, roughly. And so there's an infinite number of you have to specify with infinite precision to send the qubit state. But here it can be sent which has 2 classical bits of information. Okay. Of course, at some point you had to send the qubit, right? The previous entangled qubit, but it was another qubit. Okay, so it's another that you sent before, and then after you send that one, you send the actual qubit message you want to send. Is that clear? Well, so it's a little surprising. And so one question is how this qubit travels, but another perhaps more relevant question is the following. So Romeo and Juliet, let's read this. And so Juliet said, well, why don't we set up some very highly entangled state, okay? And then Romeo jumps in, and then he gets thoroughly mixed, and then we'll be able to extract Romeo on the other side, okay? That's possible according to quantum teleportation. But Romeo didn't like this because he didn't like the idea of being thoroughly mixed with the qubits. It looks like putting a blender and being thoroughly mixed. But Juliet said, well, you'll be reconstituted. You'll forget that you have all these problems there. You forget that you will be killed. But he said, no, I don't like this very much. Okay? I don't like this. Okay, so but then they read this other paper by Dow, Jeffries, and Wall. And what these people said is, well, let's imagine we do the same type of quantum teleportation thing, but now instead of having some random set of entangled qubits, let's say that what the entangled pair that we have is an entangled pair of black holes. So imagine we have 2 quantum systems that have a gravity description, and then we have 2 entangled black holes. And then what would quantum teleportation look like in this picture? Well, we said that the entangled black holes will look like roughly like this Penrose diagram of this diagram, space-time diagram of the Schwarzschild solution. And then the message would be something that you send in from this side. And if you do nothing, the message will go into the singularity and not come out. But the idea is that you can do a measurement here. And in this geometry, the fields here and here are entangled. So if you do a measurement here, you can take advantage of the results of this measurement to send a negative energy pulse into this black hole. You couldn't do that if you only knew this. If you only knew information about this side, you need to know something about this side to be able to send negative energy. But if you send negative energy, then the physics of time delays in general relativity says that you can have a time advance. So normally when light goes near a massive body, near some positive energy body, it gets some small time delay. So this is called the Shapiro time delay. It's related to, and it's been tested and so on. But if you had some negative energy, it would have a time advance. And time advance means that this can move a little bit further to the right and be able to go out to the other side. So this is how quantum teleportation looks like in this setup. So you send a message, you send the classical information, and then the message comes out. So the message is really going through the wormhole in this picture. Okay, so now Romeo and Juliet. Something important is the following. What does the message feel as it's going through the wormhole? So the message is falling into this black hole, and it's traveling as if it was in empty space, right? And here it feels the shock wave, So this is some kind of shock wave, that if you arrange it to be spherically symmetric, then it has no effect, and it also, the message doesn't feel anything particular when at that moment. And so it can be completely arranged to be painless. And so this is how Juliet convinced finally Romeo to actually, so they set up the same two black holes of the beginning, but now Romeo jumps into the black hole and arranges for a measurement device that would measure the Hawking radiation coming out of this black hole, and send the classical information to Juliet, who will then apply some transformation, send a particular wave into the black hole that will extract Romeo on the other side. So that's the story with the nice ending. Okay. And now the point of this story is not so much about Romeo and Juliet, but about the two drastically different pictures that we have for thinking about this system. So one is the quantum mechanical description, where you have this thorough mixing of the qubits and so on. And the other one is the space-time picture, where it looks like nothing is happening, right? So now, okay, so it's time for the end of the talk. So I think I like to say that the take-home message should be, well, of this second part of the talk, is that the entanglement pattern of the quantum system seems to determine the bulk geometry. And the precise details of how this works are still being worked out. We're still making progress in this direction. And that these ideas are important for understanding how quantum mechanics and black holes are consistent with each other. Okay. So I had some further conclusions, but maybe I should just end here. Thank you.
Thank you, Juan, for this interesting talk. So are there any questions?
How accurate when you decide black horizon? Is it black length or width of horizon?
Yeah, so the horizon is a classical notion for a classical geometry. So the width is 0 in the classical limit. Well, physically, the horizon is nothing. It's an imaginary surface because you can't measure the horizon, right? So someone who's falling in, you can't really measure. If you try. Well, time stops if you are accelerating infinitely, right? So if you are staying at the fixed location, then it will look to you that time stops, and you would feel a very high gravitational force. And you also feel a very high temperature, an effect that Bill Unruh here has discovered, and is related to Hawking radiation also. So if you try to do that, you will be fried. It will be very difficult to do. Yeah. But roughly something that people have discussed is that you cannot talk about the horizon when this temperature is higher than the Planck scale, for example. And so that's normally taken to be how sharply you might expect to be able to define the horizon. You can certainly not be at the Planck, closer than a Planck length from the horizon. Yeah.
This is big nonlinear system.
Yeah.
With many particles in it.
Yes.
We know many degrees of freedom, and we know that normally such a system has developed, even in classical and quantum mechanics, developed what they call deterministic chaos.
Yeah.
And how is possible to distinguish between deterministic chaos and real chaos?
But what is the difference?
I mean that we can make such a thing as Poincare and cross, that you see each time something new and
Right,
average over
Right. Yeah, I think yeah. So that's a good question. So I think let me rephrase the question slightly. So if we have that the black holes have this very large entropy, right? And so for systems that have very large entropy, it is difficult to see whether information is being preserved or not, right? Because even if the system preserved information, it would be very hard to notice. It's a question, some of these are questions of principle, whether in principle you could get it. Now in the context So let me just give you an example of something very sharp where you see the difference between the unitary and non-unitary system. So for example, if you throw a perturbation into a black hole, right, that is isolated, let's say you put it in a box with reflecting boundary conditions. So so it's a thermal equilibrium initially. Now you send in a perturbation. According to general relativity, this perturbation will decay. And so in the far future, the effects of the perturbation decay exponentially, and so at very long times you won't see anything. But in a unitary system, that cannot happen. So because there's a finite number of levels, energy levels, and so on. And so what should happen is that at very long times, you should have some non-zero correlation. So the two-point correlation function or the effects. So if you measure that same variable at some later time, there will be a non-zero correlation due to the fact that you sent something in. But it would be very small. It will be proportional to e to the minus the entropy. So that gives you a notion that these effects that can distinguish between unitary and non-unitary are very small. They're effects, for simple observables, they're effects of order e to the minus, whose size is of order e to the minus s. So this is just what you expect. So if you want to check that there is some particular correction to a particular correlation function, it should be a tiny effect of this order. At this order, there is something that you have to take into account that is not normally, but that is important, which is the fact that the geometry, there could be other geometries that contribute beyond this one to the process. So when you have a path integral, like the Feynman path integral, but now we're summing over geometries, and there will be other geometries that contribute. And it's been, there was the idea that perhaps these other geometries could fix this problem. And in the context of very simple toy model, very simple two-dimensional gravity theories, recently this has been, well, there was a calculation by Sad, Schenker, and Stanford where they showed basically this picture was correct, that this two-point correlation function at long times have statistics and properties which follow from the sum over geometries and are in accordance with the expectations for unitarity.
So for any finite time, you can resolve it, yeah? But if the time increases, you move to more and more resolution.
Yeah.
More stronger resolution each time.
Yes. Questions? Yeah. Well, whatever. Yeah.
So you presented universality, this idea.
Yes.
So as you're talking about this correlation,
Yeah, that's important. So that was when we were talking about classical black holes. So classical black holes have this no hair, are very simple. Quantum black holes have a whole atmosphere of, let's say, Hawking radiation. So there is a quantum state around the black hole. And depending on the microstate of the black hole, so the quantum state of the system, those would be slightly different. It would be thermal only in average. Well, I guess, but I mean, one hair it does have is the state of the quantum fields outside the black hole. This is part of it. It's hard to get the counting of the entropy just with this, because the entropy of the Hawking radiation, the quantum state of fields around the black hole, if you were to compute it, you would get the ultraviolet divergent answer. So when you go very close to, we mentioned before that the temperature gets very high when you are very close to the horizon. And so that implies that the entropy will be formally infinite. So if you cut it off at the distance of order n Planck, you get the area formula, but with an unknown coefficient. So this shows that this radiation has something to do with the entropy of the black hole. And in fact, if you compute the quantum corrected entropy, there is a contribution from the quantum fields explicitly. So the full formula for black hole entropy is area plus the entropy of quantum fields. Well, nothing that I have said depends on could be said even including this soft hair discussion. So the soft hair discussion is some ideas for how to distinguish different black hole microstates and things like this. Yeah. Well, the soft hair, yeah. Yeah, that doesn't affect. So in the cases, the main cases I discussed this correspondence in these black holes that were living in a negatively curved space. In these cases, this soft hair is not relevant. So that's a property of Minkowski space. So that might be relevant for black holes in Minkowski space. They're definitely not relevant for black holes in ADS space. So yeah, I mean that's the soft hair discussion is something that is relevant for black holes in flat space. Indeed, the energy levels of different black holes. Well, I should emphasize black holes have a huge entropy, and that implies that the energy spacing between different black hole states is very tiny. It's e to the minus s. It's very small. So if you are going to ask questions that depend on the details of the energy levels and so on, you have to have control over this black hole with this precision in energy, right? In particular, if it is in flat space, you have to go to very, very long distances in flat space to, well, at least that's exponentially large, to be talking about the energy levels of the black hole confidently. So it is conceivable that this, I mean, it's only reasonable that this soft hair discussion has to be, well, we have to take into account the soft hair to discuss black holes in flat space. But it's not clear to me that it's an essential property of black holes because the black holes could be in anti-de Sitter space. They could be two-dimensional, for example, where these issues of soft hair are not relevant. So, or at least not obviously relevant. So